our first day seminary. Let me introduce you our today's speaker, Kossak. It's a professor emeritus at the City University of New York, and also a member of the program committee of tomorrow's conference Horizons Zoom, which is dedicated to the legacy of critical thinking. Kossak is an author of several monographs and many articles where he dealt with questions with mostly with model theory and the problems of Peano Arithmetics and definability. He also worked on the interrelations between mathematics and philosophy and art, so it is a good match for our seminary. And in his today's talk, he will be dealing with the problem of definability and representability by the means of the first order logic. So, the stage is yours.
Thank you very much, Jan, for this very kind introduction. I'm really very happy to be here. I love this room. It's a real seminar room. I understand it's being broadcast somewhere, so I will try to sort of speak slowly. Really, I apologize for not preparing slides. I had a conversation about it. And I thought, during the pandemic years, we all got very tired. So, yeah, maybe I don't need to say more. And so, last semester, Karel also is my colleague from City University. There was not a single talk at our seminars that we would have Zoom or slides or all talks with chit-chat, and it was a great pleasure. Anyway, I'm not quite sure whether what I'm going to say will be a great pleasure, but at least the mode of delivery will be sort of slow and things will be happening. And I understand this is a very mixed audience. So I want to sort of first set up the context, and some of you will know very well what I'm talking about, although maybe there were some special angles of what I'm trying to say. But as Jan said, I'm a model theorist. I specialize in model theory of systems, formal systems of arithmetic, but I'm interested in all kinds of things around foundations of mathematics. When I was a student in Warsaw, that was close to 50 years ago, when we had two divisions. There was division of logic, and I think the division of logic that was led by Helena Rashowa, that some of you might know about. There was a famous book by Rashowa and Sikorski of mathematics, of metamathematics, and was very influential for some directions of developments in logic. But there was another group led by Professor Andrzej Mostowski, and there was a group of foundations of mathematics, and they were separate. And this group, Professor Mostowski and Petro Pinka, they knew each other, and both groups of logicians, set theorists, had frequent contact with one another. Pavel was visiting now and then. You were. Sorry? We were visiting Warsaw now and then. Yes. And I don't know about Karel here.
Was there once?
But other people visited more often, so there were very frequent contacts. But anyway, so this is about foundations of mathematics, and the way it was understood in this when I started studying it, it split into four disciplines. So one is set theory, the other is proof theory, and then there's computability theory. And then there is model theory. Okay, and so what is this division? Well, first you answer very basic questions, and they are both technical. In the Polish school, everything was very technical. They treated everything, especially set theory. It was much, in 1918, when Poland was reconstituted as a nation country, there was a group of mathematicians who gathered at the University of Warsaw, and there was this young influential fellow named Janiszewski, and who sort of organized the development of the department around. They had topics that were sort of important topics, some things that were happening in mathematics at the beginning of the 20th century. and they decided to concentrate on set theory and topology, and they were extremely successful doing all of that with names like Banach, Sierpiński, and many other names that you might have heard. But anyway, so here the question to answer is, well, what is a set? Right? And you start with this question, and then you will move on with some technical stuff. And then there's proof theory. And this discipline is probably like about 100 years old. There are roots around, in particular. Yesterday at the conference, there will be from Kueker-Reyes and the influence of Bolzano on set theoretic developments, but it's really the Cantor in Germany, no kind of developments later. First what's called naive set theory, and then axiomatic set theory with Zermelo and many other people, but it's no longer than 150 years old. But now these two, I would say this is about 100 years old. And I think I don't really know if you have heard anything about Hilbert's program. It was David Hilbert, who was one of the two most influential mathematicians of the early 20th century. The other one was Poincaré in France. And in 1925, he formulated what's known as Hilbert's program. It was this kind of, not Hilbert's 23 problems for mathematics, it was 1900 Congress of Mathematicians, but he formulated this program for foundations of mathematics for various reasons, and and whatever he wanted to achieve turned out to be not achievable. It's a complete failure, although there are some ways of looking at Hilbert's program in positive ways. But we wouldn't have proof theory, and we wouldn't have computability, that used to be called recursion theory, without those problems that Hilbert set up. And it really motivated much work. So this is about 100 years old. And I think we should be celebrating this year 100 years of Hilbert's program. I don't know, have you heard anything about any celebration? There should be. No. Anyway, because we wouldn't have AI without Hilbert. We wouldn't have anything without Hilbert 100 years ago. Maybe it would have happened some other way, but it was an incredibly bold proposal for foundations of mathematics, including things like every mathematical problem is solvable. You just have to raise the level to high abstract that's enough abstract, and then you look down and you can solve any problem you want. Either you solve the problem or you show rigorously that the problem is unsolvable for some reason. So this turned out to be completely sort of a science fiction. Nothing like that happened. Things turned out to be much more complicated. But now I'm a model theorist, so I'm going to talk about model theory. And this is really strange because this is probably not more than 50 years old. So the model theory that is being practiced now was really formulated that way around 1940s, 1950s. And there were two schools in the United States, but they were both on the East Coast. It was Abraham Robinson at Yale, and certain way of thinking about model theory. And then on the West Coast, it was Alfred Tarski, an immigrant from Poland who started the whole school of model theory at Berkeley. And again, at these days, it's one of the most vigorously developed areas. So what I'm going to talk about, I just want to tell you a little bit about what model theory does. What is it we do in model theory? But any of these sort of areas are extremely difficult to popularize. Anything that you learn in school is not preparing you for the kind of mathematics. I remember when I became a student in Warsaw, I wasn't really good at mathematics, but I was good enough to get accepted to the mathematics program. And I thought it would be something like what we did in school, some geometry, some algebra, but more complicated. But it was nothing like that. Everything was on a much more abstract level, all kind of interesting concepts, but it's extremely difficult to sort of to talk about it in a popular way. There are some good popularizers of mathematics, and I would say Pavel is one of them. And I know because he wrote a book, which is somewhat popular. But it's hard because we have to have this sort of background. So I will try to say things about model theory using examples. I will not make any big formal definitions. I will just show you some examples of what we do and how we do it. And as we talked about before my presentation, I welcome any questions at any point, because I don't have any kind of goal to reach. If anyone wants to ask something, please do. So the important thing that we start with as what will happen in set theory this sort of acceptance of actual infinity. So we study infinite structures. There is a separate discipline, model theory of finite structures, which is also kind of a very respectful domain of research. But what's really new and very attractive is a certain point of view on how do we study, how do we analyze infinite structures? And I was thinking, so what is the easiest example that I could sort of talk about? So the example that we have an infinite set of points. And the other points, but again, also already some kind of this set theoretic outlook that we consider it as given, it's infinite. Okay, so it's complete infinite set of points. You can think of those points as being numbers. At some point they will become numbers, but at the beginning just points. So it's already a structure, okay, because every structure has a domain. So the domain of my structure will be this infinite set of points. And I will assume later that it's countable, which means I can count, you can enumerate those points using natural numbers. The first one, second one, third one, so there are larger infinities, but this is like the smallest infinity. This cardinality of this Allen zero, counter wanted. So okay, so now I want to have some structure. So I will have a relation. And symbolically, I will use symbols now. I will at the same time explain this first elements of first order logic. And in first order logic, we will have the usual logic that you all know, which is a logic that uses Boolean connectives and or not, and two kinds of quantifiers, existential quantifiers and universal quantifiers, and that's all. Okay, so we have statements about certain objects, and this is the only statement, and those facts about structures will be expressed, if possible, using this first order logic. So to express those facts, well, you have to sort of identify some language. If you want to talk about a relation, I give you the name. It will be a name for the relation. It will be a binary relation. It will bind pairs of numbers, and I would say that the two points are related. And this is sort of informal. If y is x plus 1, this is very informal. I'm thinking now about these as numbers, but this is completely from outside. This is really a simple graph. In graph theory, this is called a directed graph. Okay, so between points you can have edges, and the edge identifies which point is related to which one and is directed. So the first point is related to the second, but not to the first. So it's a directed graph. So this is the simplest structure that it's somewhat non-trivial that I was thinking about sort of discussing. Okay. So you look at this structure, and I said, so we consider this language of first order logic not just something to formalize proofs, because this is done in proof theory, but something in which I express facts about structures. What is it that we can observe about the structure that is expressible in this first order language? So one of the things, what is the first thing that you observe? If there is a first thing that you observe. Like if you want to explain to somebody, oh, this is the structure that has such and such properties. So what kind of property sort of suggests itself instantly?
Which one is the first one?
Exactly, there is a first one. Okay, so clearly this is this ordering that sort of goes to infinity somehow, and it's interesting to see how this can be expressed. But clearly there is a one, so that it's a beginning. So we say, well, there is some x. And maybe I will use y because of this sort of. There is some y. No, so there is an x such that for every y, it is not true that x follows, that y follows. For every y is not, x is not a successor of any y. Okay. So that's clearly a property, okay, and it's expressed in this formal way. It doesn't matter that I use symbols. Is this right? Roman is.
I'm wondering where this property comes from. What is the primary thing? Because, of course, the way you drew it, that property holds. But if you just write the binary relation, and if the binary relation is total, it doesn't mean the property holds because it could be a circle. So
Right. So,
where is it coming from?
Or it can be all integer numbers.
no, right. So we could be looking at a different structure. That's what we're saying, but we're looking at this structure. So we're trying to express properties of this structure and not some other structure. Okay, so okay, so there is one, but there are other. So for example, we know that now if this happens, that and I will not write it, especially because it's online. You can write it something even more specific about it, because not only that there is such an X, but there is only one. Right? First one. Okay, and no other, because there could be two lines like that. There will be two, but there's just one line. So this can be expressed. And I will not write a whole sentence, but there is something that can be written in first order logic. This exists exactly one. Okay. This means that for every there is one like that, and every other that has this property is equal to this one. So there is a longer first order sentence that says there is exactly one element that doesn't have the successor. Okay. So and now if something like this happens, in logic, I just have one relation symbol, but I can have other relations and I have constant symbols. I can identify certain constants if I want to talk about them. But if something like this happens, if an element can be defined, that I don't need a constant for this element because I defined it. There is a definition actually, this sort of definition, this is now not a sentence, this is a formula. It defines a certain set. This is the set of those x's that have this property. Okay, they say, I'm looking at all possible x's that have this property, there's only one. Okay, so that allows me to introduce the name for this, that in formulas I can always translate later by sort of using longer sentences because, I can identify this element. So let's call it 0. Right? But I'm not extending my language yet because I don't need it, but I have a name for this one element that has this property. So another interesting property is that for every x is not 0, or using sort of formal symbols, it is not true that x is 0. So every element except for this one has both a successor and a predecessor. Okay, so then there are x1 and x2 such that s1 x and s x. Okay, so again, so in this formal way, I have this the point here that when we teach it, so you introduce the first order logic and you explain how can you form, and I'm sure you must have seen it somewhere. But the point is that very simple facts. So here I'm looking at the structure and I observe some very simple facts. And the whole point is that they are expressible in this language, but sometimes to express something in this language takes a longer sentence. Because, for example, if I didn't use 0, then I would have to say that, for every x that happens to be the x that has this property, this happens, so it becomes even longer. But the whole point is expressible. Okay, so this says every other element has a successor or predecessor. Okay, but now look, but there is something else I can define. I can define something I would call as 1 of xy. And here I would say that this would say, can you see it? And I write the block here. So I would say there exists x1 such that s x1 and s x1 y. Okay, so like here, if I have these two elements, it just says that between these two elements, we can get from here to here, going through an element in between. So there is one element in between. So it's something like measuring a distance. How far is it from one element to the other? So use a formula that defines it. So you can imagine that I can write a similar formula as n of xy. And here I will say there are n elements in between, and it's all first order definable. And by the way, and those of you who are more philosophically minded, this is very powerful, this logic, partly because I can write formulas with any number of variables. And do you know whose discovery that was? That this is really something that's needed. It certainly wasn't Aristotle. No, there was Aristotelian logic, but this thing that you can talk about formulas with an arbitrary number of finite number of variables. Who was that? Yeah, Frege. And it was Frege, and it was not that long ago. You see, so that's why model theory is only 50 years old, and Frege is about 100 and something years old. And but this turned out to be actually crucial. That even though you talk about a simple structure, you talk about properties of elements, what matters are relations that you can define, using a large number. Like here's another binary relation, but you can define ternary relations, quaternary relations. You can talk about all kinds of finite sequences of elements on the structure in this language, which turned out to be crucial. Okay. Now, all right, look. So the question is now: is there anything else that can be said about this structure?
Yes. Don't you want to say that x1 and x2 are unique, for example?
Well, no, that's right. No, this is right. So, thank you. But yes, what
Because you could have a tree.
No, currently, I'll put it right now. I sort of, clearly, so this is true about these two elements, but it's true about any other two elements if one is on the left and the other on the right, because there will be more elements. But then, okay, so now this is awkwardness of first order logic that I don't need another property, but I just add to it. And for every z, I say that is in between is actually x1. Okay, so every z it is, between x and y, it's that x1. Okay. So this part says there is at least one element in between. And this part says, well, but there's only one. So and then you extend it by saying, oh, there exactly n. But this is this awkwardness because now we have n variables, so the sentence becomes even longer and longer. But the whole point is all quite expressible. So, but now if you look carefully at this, you will say, oh well, there's probably nothing much more that we can say. This is such a simple directed graph that there is nothing much that one wants to say about it. It seems like when I said all of this, and you give those instructions to AI, well, the picture that you will get will be what I just drew on the blackboard. Or is there anything now that I'm missing again? Right. So there is something here, the uniqueness of the successor I could sort of include in this.
And also that the successor is different from the predecessor. Is that included somehow?
Right, and then right. So this is also there is s of xy, then x is not y. Okay, so that again I can write it, but it will be like maybe one or two more sentences, but it will be like a complete description. And this was actually one of the original things in model theory. If you look at certain structures, and you look at some kind of logical descriptions of all the properties that already axiomatize the structure, that anything you can say about that structure is already somehow the result of those axioms. And the way you prove it model theoretically is that if you make a list of those axioms long enough, then you would say, well, the only structure that has these properties is this one. Okay, that would be great. All right, now, but unfortunately, this cannot happen. Okay, so there is a theorem that I consider I feel like a fundamental theorem of model theory, although it's never listed as a fundamental theorem of model theory. If I have a structure there, which means a domain with some set of functions and relations on it, and the domain is infinite. So we say that if it's infinite, but understanding that this is a whole structure comes with with all those things on it, then there is n such that, and I will write symbols that n is an elementary extension. This means elementary extension. And what it means is the following. What is an elementary extension? This is something I drew on the blackboard yesterday too, but this blackboard is much better. So I can do. No, because it was plastic. It wasn't even. The pictures were terrible yesterday. I can do a little bit better. Okay, so what is elementarity? Is that you have some, okay, this is the domain of the structure M, and this means you have an extension. So you extend this to a larger domain, and elementary means that if you have any finite sequence of elements from the ground model, then the following happens. And again, I don't like repeating myself, but I said it yesterday, so only Zuzana and Talan were there. So
No, Christian too.
oh,
All right, do more.
no, but okay, so you will see it again. It's not the big thing, but this is a fundamental thing that now I will write something like this. Now, what is this? This is the symbol that I'm told that, you know, when we start using this in model theory, every page has about 10 symbols like that. But this means that something holds in this structure. And what is it that holds? That you have a finite number of elements. And this is a property, a first order property that has the number of free variables equal to the length of this sequence. And this actually holds in the structure. Formally, there is something called Tarski's definition of truth, but it's a very natural definition. So it's based on how complexity of formulas. So, for example, if phi happens to be a conjunction, then the conjunction is true if both conjuncts are true. And if phi happens to be an existential statement, then it's true if there is a witness that makes it, and so on. So this is a very straightforward definition. So this is like the whole truth about the structure and all elements in it. What's true about all possible elements in the structure? And an extension is elementary if it doesn't change. If this truth doesn't change, you go from the smaller structure to the larger. So this happens if and only in atoms. Okay, so in particular, this applies to all sentences. There are no parameters, it will be just sentences. So whatever is true about M will be also true about N. But it means, well, that this is actually something that was proved first without this terminology by Tarski around 1934. Tarski constructed an elementary extension of the standard model of arithmetic. The standard model of arithmetic would be natural numbers with addition and multiplication. And there was a construction, this is an ultra product construction that gives you this elementary extension. And this is called a non-standard model of arithmetic, because this elementary extension necessarily must have a larger domain. So it will, and it's easy to check, then this other model that looks like natural numbers must have infinite elements already. So something happens there. And but even though you have those infinite elements, whatever was true about natural numbers, it's still true about this extension. So like there are infinitely many primes here, there will be infinitely many primes here. If something holds here, something holds there. Every equation that has a solution here will have a solution here, if and only, and so on. So this is something that mimics the original structure. It's called non-standard because we really don't want to study those models. I do, but not everyone wants to. We want to study the standard model of arithmetic. But we have all those extensions. And for Skolan, the idea was not that it was happy. Oh, now we have this source of new rings, or you extend by adding negative numbers, and you have a new ring to study and all of that. Now, for Skolan, it was the thing to say, well, first order logic is deficient. There is no way you can identify a structure up to isomorphism by its first order properties. Well, it's not happening always. Because, for example, if this is a densely ordered set, if this is instead of rational numbers ordered by the regular ordering of the rational numbers, dense, linearly ordered set, and you can make an extension that of the same cardinality, then it's known that up to isomorphism there is only one. So what you get is an extension, but it's an isomorphic copy to what you started it. So not always you get something new this way, but the whole point is this can be iterative. So now set theory enters, and you can start with a countable model, small model, and keep doing this. Keep doing, and then you can get a model of arithmetic arbitrarily high cardinalities. So clearly not isomorphic, not an intended model. Any cardinality there exists, no matter how large cardinal number, you get a model of arithmetic of the cardinality. So by iterating this one theorem.
So in this, for these rational numbers, this real numbers is one of those extensions. So
No.
The standard real numbers.
Yes, right. No, but standard in a sense, but only consider if we're talking here about rational numbers with the ordering. So it is true, although it requires a proof. It's not a difficult proof that you get them. But
there are other extensions.
No, there are other. Actually, there are lots and lots of non-isomorphic ones.
Yes, yeah.
If you get a countable one, it's isomorphic to what you started. Because there's only up to isomorphic, there's only one that's linearly opposite. But this can be done in again. For example, if you take something like this, you take rational numbers and you add something like you think rational numbers appended on the left and the reals, okay, to the right. So you get something that's not isomorphic because it has this part here that's countable on this side. So this is not isomorphic with that, but it also gives an elementary extension. But you just add a copy of rationals at the end of the wheels.
Yeah, we just have the ordering, no. Okay.
Right, no, we're not talking about addition. No, we're just not talking about ordering. When I talked about column, it was in the language of the rings. And
so I'm thinking about this object that every rational number, I put a line. So I have such a structure, but then this is not ordered. So somehow
no, but it can be ordered. We can do that too. No, but what I discussed here. No.
So what was this symbol plus?
Just intuitive that you have rational numbers here, and the ordering is such they're on top of it, the real numbers, and every real number from here is larger than. Okay, that's informal. Okay, so we're not doing anything else. Anyway, so let's go back to the example. Okay, so if the fact is true for all possible structures, it is true for this one. So let this be my M. Okay, and I want to see what then this elementary extension look like. So I have M and some elementary extension. And so it must contain the original graph. It's an extension, so it's so this is something now, and I will start calling them numbers because they look like natural numbers with a successor operation. But now I must have something about it. But now look, what's true here, all those things I listed here, true. Okay, so in particular, well, there's only one number that doesn't have a predecessor. So that's still 0. I'm not adding any new 0 anywhere. Which means that if I take there has to be something above, but if I take something that's not 0, it must have a successor and a predecessor. So there must be something here, And also, from elementary properties, none of those can be anywhere here because it's an elementary extension. So every element has a unique successor. So all those elements already have their successors. So when I do those successors and predecessors, they have to be new ones. Okay, so if you look at it sort of a little bit more, then you see that this has to be some type of copy of Z. Okay, an infinite line that goes to infinity in both directions. Okay, and the fact is that I didn't tell you how to get those elementary extensions, but it can be proved that this is an elementary extension. Okay, actually, but it's not completely trivial. Okay, this is not a simple exercise. It requires something that for those who know, for example, the simplest group used the Ehrenvoigt-Frese games to play games for these kind of structures, and because it's simple, we know exactly what's going on, but there's some kind of a property that's non-trivial. Okay, now, but if I got a one like this, I can extend it again because every structure has an elementary extension. So there will be a new element somewhere, and I can continue. So this way, I can get C1, C2. Okay, any number of those Z chains, and I can continue doing this countably many times. So I can I can actually even have infinitely many of them. But now the thing is this, that what we do in model theory, we have something that we call the theory of a structure. So here the theory of a structure, have a theory of what it is. This is the set of all true sentences in that structure. So so if a structure is as simple as this one, then I can write the axioms. And this is probably not a complete list yet, but it's not difficult to come up with a complete finite list of axioms that completely axiomatizes the theory, which means any other true sentence in the structure will be a consequence, logical consequence of those axioms. But we don't need the axioms. We can say, oh, I just take all of the true sentences. This is the theory of the structure. So because the extension is elementary and also has the same theory, all these models have the same theory. So this is some theory T. So on one hand, so we do things in both directions. You have a structure and you want to see what is the theory of the structure. And in the other direction, if you have a theory T, then you want to know what are the models of T. Okay, you want to classify them somehow. You want to see, how many different models are there? How many non-isomorphic models are there? How all of this? And in this particular case, this is a perfect example of a theory that's completely classifiable, because what I drew on the blackboard is a complete classification. That it turns out that all countable models of this theory, they look like that, and each has a dimension. The standard one will have a dimension 0, and then you count the number of those Z blocks. If there's one Z block with dimension 1, dimension 2, dimension 3, or dimension infinity, and that's all. And then it's not difficult to do all of that, although it all requires some work. But this is like a picture of what we do in model theory. And in model theory, one can start with any structure, and they say, okay, let's see, can I classify somehow all models that look like this one according to what the theory is? So now, are there any questions? Because now I want to use this, that once you have this fact already, I want to use it for something else.
So you had this construction up to infinity, and you are saying this is the single one. So can one take all this and add it after that? Something?
Right. No. So the thing, there are two things. You can get these structures by applying this sort of what's called the compactness theorem. So you get these many models. On the other hand, you can prove using other methods that anytime you take any bunch of Z blocks attached, and how is the successor relation defined here? Well, like on the integers, any collection, it will be an elementary extension of the standard model. So it could be countable, it could be uncountable, it could be anyone. But the interesting thing is that there are countably many non-isomorphic models, and they can be classified by their dimension 0, 1, 2, 3, and so on, infinity, Aleph 0. But if you go to uncountable models, up to, for every uncountable cardinality, it will be only 1. Because they all will be isomorphic to one another. Because you have a bunch of the Z chains of given cardinality, take any other one, and just match the Z blocks one with the other. So a theory like that is called, this one is not Aleph 0 categorical, because it has many non-isomorphic models, but it's uncountably categorical. It's not categorical in an uncountable power. So it's already kind of themes. These are the kind of themes of model theory. Okay, but I want, let's see, I want to see how I'm doing this time. I'm doing too bad. So. Look, now the thing is this. So for Scotland, this non-standard model of arithmetic, it was important because, this standard model of arithmetic, this is like the natural object of study. No one wants to study this graph. We know everything about this graph there is to know. It's not really the point. The point is to use this graph to explain certain properties. But now there is something interesting that happens, which is if you think of this graph as the successor relation on the natural numbers, you see, if you're a computer scientist, I could have mentioned this yesterday, that you know that the successor operation on the natural numbers already determines addition and multiplication and much more. Okay, there is unique, there are what's called recursive definitions. Once you know how to add one, so maybe I'll show you this. I'll show you this for linguistics. If you want to know how to do n plus n, but how do we know how to add numbers? Computers add numbers this way. First you say what is n plus 0, right? N is m, and then suppose that you know what is n plus n. Okay, so you know already. You have computed this already. So what will be n plus 1? How to do addition of the larger number? Well, this will be n plus n, which I already know, plus 1, which is the operation that I'm allowed to use, the successor relation. Okay, so just adding 1 already completely determines addition. And once you have addition, there's another recursive definition that shows you how to multiply numbers. Multiplication is a repeated addition. So you start, right? A similar. So that's really foundational computer science now, that by just adding 1 to a number gives you all these things. So this structure has that information already. Okay, so now the unpleasant thing now, and maybe Scholar, if he noted that he would be actually interested in it, that there is something simpler that is completely determined. We have this infinite line, and when you look at it, it determines the ordering. This is not an ordered structure. In an ordered structure, if you take any two elements, you should be able to tell who's larger, who's smaller. Here I only have the successor relation. So if I ask you, well, is this smaller than this one? Well, you can say, oh, it is because there is one element in between. But what if I take the next one? Or you say, oh no, this is smaller because there are two elements in between. But if you have still of this line and you go to some kind of some A here and some B here, how do you say that A is less than B? Yeah, how to express that? I want to say there is some number of elements in between, but this number is not specified. So you can say that there are many elements in between for every given n, but it will be a different sentence, different formula for each n. And in general, you may think, oh, maybe there's some clever formula that you can sort of come up with.
I'm sorry, isn't that circular definition to define that B is bigger than A? You say that something is in between, and in between means that it's bigger than A and less than B?
No, you see, you're asking the same question. We know who's bigger and who's smaller because we know the structure. This is a line. You know who's first, who's second. It's a line, at the ticket office. You know who's first. You know that. The question is, how can you say that in first order logic? How can you define the ordering? So far, you only know who's first, who's second, who's third. Okay, one by one. And you want to say, now I take any two numbers, and how can I say, using a logical sentence or a logical formula that will identify the fact that we see, okay? It's not defined in any way. It's a property of this structure. When I look at the picture, I know that A is less than B. It is less than B, so what? I want to write a sentence that expresses this.
So right now we don't have non-standard numbers.
No, we don't. So, no, we don't. But we will have them in a moment.
But of course, you can define it in cursive, which just start with it.
I thought you. No, but that will be my next point.
But from this model that I highly
Oh no, you're stealing my This is something I'm going to say. No, you're absolutely right. But this is something that I find actually quite interesting. And
so the problem is that you need some certain number of those that are in between. You have to say n.
Right, you have to say n, and if
you want me to say without using the n.
Right. And what Karel is anticipating,
and you do not accept the answer there exists an n such
right, because there exists an n. Right, because and followed by what? Okay, there exists n.
There exists an n and n points such that.
No, but how do you say n points?
N elements from your set.
But how do you say it in this formalist? Right? That might be, let's clarify this point. Okay, this is not one.
So this is some restriction on the language.
Exactly, not really not the restriction of the language, of the expansion of the language. The first order logic doesn't have the facility. Exactly what you say. There are x1, xn points in between. And now I showed you that for every n, we can write the sentence, but as n goes up, those sentences get longer and longer and longer. So this is, it's not, but it's not obvious. Maybe there is some clever sentence that expresses this. And in richer structures, this may happen. But I will prove to you that you cannot do it in this structure. There is no formula whatsoever that defines the ordering. Okay? I will prove to you. Okay, so no matter how hard you try, no, but you have to right to extend the language when you can express things like that. This is a very crucial point. In arithmetic, for example, it can be done because in arithmetic there is coding of finite sequences. So in arithmetic, there is a sequence of length n, such and such. And I was
just thinking there exists a finite n such that.
Exactly. Because you take this n that codes the sequence and the sequence of successors.
Okay, so we are
and the same, you know. So in full arithmetic, just for the successor, you define addition and multiplication and much more because you can convert recursive definitions to explicit first order definitions, but not for this structure. But you know, but I will prove it to you. And the thing is this: I find this proof very kind of telling because how do you show that something is defined? Now you have this relation. A is less than B, and look. We know what it means. It's just that we see the structure and we want to identify, you know, some formula that will identify this relation. But it turns out that this relation is external to this structure because it's not definable in it. But if I'm showing that something is definable, then I have to find the definition, and I write a complicated definition and I say, oh, it works. But how do we show that there is no definition? That's the whole point. It's the same thing, you have an equation, and if you want to solve an equation, then you sit down and you solve the equation, here's the solution. But how do you show that the equation has no solutions? We have to have some deeper knowledge, you know, what are the possible means of solving and this and that. Unsolvable problems are much harder than solvable problems. So here the unsolvable problem, it's not an unsolvable problem, it's simply there is no formula that will define the ordering. Okay, but look, but I will give you a complete proof, and maybe this will be enough for one day, or I can do more, but let's see. So there is something, if you have any structure, but so suppose you have some structure with some binary relation, which is like this one. So, and I will say what it means that F is an, okay, automorphism. Or if I, in popular talks, I would say a symmetry of a structure. Okay, what is an automorphism of a structure? I think a symmetry of a structure. Well, so f is a function from m to m. It is 1 to 1 and onto. So it's a permutation. You permute the elements. And what it does, it preserves the relation. So the condition is that for all a and b in m, a is related to b. We can only if f of a is related to f of b. Okay, so not just any permutation, but a permutation that preserves. So if you have an ordered structure, if I permute two elements, if a is less than b and you switch them, then it's not an automorphism because you falsify. Anyway, look, so what about it? It's easy to define once you know the structure, like this one. You know how to define these automorphisms. This is usually not difficult to do. We take advantage of this fact because what happens is that it's a fact that I will not write down, but if I have an automorphism, and automorphism just has to satisfy this property, preserves the relation. If there are more relations, it has to preserve all of them. But the fact is that for every formula of first order logic with some number of free variables, and the formula in the language with this relation symbol, and all a bar in M by of a bar is true if and only phi of F a bar. Okay, if you apply this permutation to any sequence, and if it's an automorphism, not only this basic relation is preserved, but also all the other relations that are definable from it. So these are all possible formulas. It tells you about what? This is a binary relation.
I do not understand this sentence. There should be another M on the right hand side with your.
No, this is the same. This I can write it separately, but we know what it means. So here
But you mean writing it with this M on the right hand side also?
No. It can be like this because
I do not understand your symbol, your T.
No, sorry. So A bar is this, okay? Is a sequence of elements. F of A bar is the sequence of images. Okay, so here we have a finite sequence of elements. Here we have
This I understand. I do not understand that F. There is this T. How do you call this T? How do you call this T?
Satisfies this.
How you read it?
True, that this is true in M.
This is true in M.
And this is a sentence.
Yeah.
In the first order language stuff. I could write it separately.
Yeah,
Which would all be true.
Yeah. No, I just want you to
Okay,
understand.
this is right. So this is
This
is in first order logic. This is also in first order.
Yeah.
The same formula twice, but here with these parameters and here with these. So anyway, so it means if you have an automorphism, logical properties are preserved. All logical properties are preserved. So let's go back to the example. So now going back to my example here, so now let's say natural numbers with the successor relation. And suppose 5xy such that all, well, I would have to say more. That first of all, okay, maybe that's enough to say that, but I will say more about it. That for all and n in n in ns, because this is a formula in the language, phi of n and holds. Now, if and only if here on the other side, because now this is here, on the other side is outside, n is less than n. This is in life, okay? Because we look at the structure and we know this relation. So m is not here because this is not in the language of the structure. Suppose it can be done. Suppose there is some formula that defines it. So this formula would have to have all kinds of properties. So for example, we know that there is something you can say about linear ordering. This is a linear ordering. So every two elements are comparable. Okay. This would be all the properties that this formula has. So for example, if m is okay, so for example, something for all x, y, and z in an S, I would have phi of x, y, and phi of y, z, then phi of x, z. So this is one of the properties of linear order. If x is less than y and y is less than z, then x is less than z. If this formula describes by ordering, this ordering has this property, so this sentence would be true. Any two elements must be comparable, either x is less than y or y is less than, and so on. So all the properties of orderings must be preserved because this phi has all those properties. So now what we're doing, we're going to n. We're going to this model. I'll call it S prime because this will be the successor relation here. Say I need just two of those Z blocks. Okay, so this is the Z block of some area. This is the Z block of some B. Okay, so you can describe the Z block as, so this is like the Z block of A. So this is the set of all those informally. This is the set of all those things, A plus N. N is an integer. Okay, which means you continue doing successors, so positive N's and predecessors are negative. So you have a block of A, and you have a similar block of B. Okay, so the block of B is B plus N. Okay, why am I doing this? Because I told you that I'm going to use some automorphisms. Okay. But the fact is that this structure is what's called a rigid structure. It has no automorphisms. Because an automorphism has to preserve all first order properties. So there is a single first element. So first element has to go to the first element. Now there is a unique successor. So the unique successor has to go to the unique successor, next successor. So this structure has no automorphisms at all. So I cannot use anything about automorphism to prove anything about this structure. There aren't any other than identity. So I cannot do anything here. But I go to an elementary extension. Okay, this is an elementary extension. So whatever is true here will be true here. In particular, all those set statements about phi. So the same formula defines on this a linear ordering. The linear ordering properties are first order. So if we look at the sort of this, so in particular, in S prime, I would have either phi. Suppose I have phi, maybe they are different. So suppose A is less than B. Okay. It could be the other way around. But it has to phi either this happens or phi of the A happens, because there are two different elements in my structure and it's supposed to be a linear, either everything is okay. But now what happens is I define my function f. Maybe I will erase these sentences, I already done. I will f from M to N. So f of x will be, it has to be identity if x is in N. Okay, this part is rigid, nothing can be moved this part. But then there will be A plus N if x is B plus N, and B plus N if x is A plus N, which is just a fancy way of writing that I'm sending this block. I'm just permuting these two blocks. Everything here goes here, and everything here goes down there. Now, so now I would have to convince you of, well, just one thing, that this is actually automorphism. Why? Because the only condition for an automorphism is that it preserves the successor relation. Okay? So here nothing happens because I didn't move anything. And here, if something is, okay, if I have a successor here, okay, these things are preserved. I send successor numbers to successor for number. So the relation is preserved. But if the relation is preserved, this is an automorphism of the structure, so must be all first order properties. So this means that in S prime, I must have phi of f of A, f of B, which means, but f of A is B, and f of B is A, which means that B is less than A, but that's bad. Okay, I violated the property because A is actually less than B. Okay, so this is not preserved, which means this is not a valid formula. I cannot have a formula like that. There isn't any formula like that. Because for any formula like that will give me a contradiction. But look, you should appreciate, I don't know if you appreciate the proof already, but you should appreciate how simple the proof is, because we're saying about all possible formulas you can think of, and say, maybe there is some very clever formula, maybe there is something that sort of will mimic the recursive definition of ordering, or maybe something, because we can talk about formulas of arbitrary complexity, but says, no matter how hard you try, you will not be able to do that. So if you have some questions now, please ask, and I just want to say something very general to conclude. And then we can talk about something else. I have a few minutes for something more general, but I will not be proving that.
Maybe an hour.
In that case. No, but I was just, no, because this is just the beginning to show you how the method works. But I'll show you now it's something that's like an interesting picture of, using similar methods, what can be proved. And maybe at the end, I will tell you what absolute undefinability is. So any questions about this part? Yeah.
There's some mismatch in my brain. So you said that you can define addition using the next operator.
Right.
And you can use addition to define less than.
True.
But you cannot define less than.
But those definitions are recursive definitions. So the conclusion is that you recursive definition cannot be translated into first order explicit definition.
Okay.
That's the whole point. In full arithmetic, yes, there is a general method of converting anything recursive to using coding of finite sequences, because the order is a sequence constructing something. But in weaker theories, you don't have that. And that's a big issue. So this is actually the argument that you cannot really code finite sequences in this theory. But you can still do, but the argument is this, that the theory is supposed to tell you something about what happens in general, and clearly, though, the recursive definition works in the standard model, but it doesn't work in the standard one, because how would you know whether A is less than B?
I have a question about the notion of elementary extension. So it means that you said it means that every formula holds if and only.
Right, on every finite set of parameters.
That not necessarily guarantees that it is the same formula in the same structure in this natural. You were using like that we know what we mean by the graph, but then making an elementary extension and requiring just the equivalence of formulas, it may happen that it's actually a different structure.
Yes.
Suddenly. Even the extended one.
But what do you mean by different? It's always a different structure. It's just the domain, one domain extends.
The restriction on the previous domain may be different suddenly.
No, by elementarity it will be not. Elementarity takes care of because the formula in particular, the basic formulas, the atomic formulas are the same. Okay, like there's this relation symbol. All in elementary extension, if you have an extension model theoretically, that's the condition that you don't change your relations.
So it's a requirement. It's not a consequence, it's a requirement.
For the extension, that's just to be an extension, right? No, but it's covered by this case. Because in particular, suppose you have this relational language. Okay, so this is a special case. You have a model M and you have its extension N. But model theoretically, I mean, no, there's that if you take, say they are both binary relations, so that for all A and B in M, I have R of A and B, which are only if in N I have R of AB, and for this I don't even need that symbol. This is what we do in algebra. In algebra we don't have that symbol. In algebra we just say this. Well,
in M or in
no. In algebra we say this, that we have this R in M, okay, and then we take AB in M, and if both A and B are in M, this happens even only that you don't change the part of the. Okay. But this follows from elementarity. Elementarity says that this holds and much more. Okay. All other relations that you define from the basic ones have that property. But the condition for the extension just that talks about the relations of the structure, right? So you don't change the structure. The structure stays the same. We can talk about it. What is this? This is, I know that.
My fear is that you told me that there are unexpressible
Yes,
properties. Right?
of course.
So
And I will show you.
What if my structure has some unexpressible
No, no, there will be lots and lots of them in a moment. I will show you what's expressible or not.
But then the extension, by the extension, I may lose this unexpressible.
No.
By definition or by proof?
By elementarity. You'll see. Okay.
Okay.
But we'll have to talk about what properties you have in mind. Because, for example, well ordering. Okay, so look. So maybe since I'm going to talk about it anyway, but I will talk about what I wanted to talk about, answering your question. Now, because I'm supposed instead of this successor relation, you have the ordering. Okay, so now you have with the natural ordering, the usual ordering of the natural number, and you take an elementary extension. Okay. So you want the properties of the ordering to be the same with all the parameters from n. So this really means one thing, that whatever this relation was, so this new one, what has to look like this, it has the natural numbers. And here it's not difficult to show. This is the same thing with the z blocks that I was using before, but now those z blocks have to be ordered as well, because this is an ordered structure. So this relation linearly ordered them. So with the successor, we had this situation that those blocks were just a bunch of blocks because there was no ordering. So this was for the n with the successor. But here, because this is a linear ordering, the z blocks are here. Okay, so you say, oh, so this is my extension. It looks different. It's not isomorphic. So for example, this one is well ordered. Okay? Well ordered meaning every set has a least element. The extension is not well ordered. But what does it mean? It's a proof that well ordering is not first order expressible in this language. Okay, so being well ordered is not a first order property, but all first order properties transfer. Whatever you can say about this ordering, you can say about this ordering and vice versa. Okay, when you say, oh, some properties, sure, clearly because you get a non-isomorphic. The M is not isomorphic to N, it's a different structure. But properties, first order properties are preserved, which is a fantastic thing.
So what is described here sounds like every real number between 0 and 1. Yeah, because I put the digits.
Right, you could do that. No, the thing, but you must have Z blocks.
Some of them are minuses.
No, but this is a discrete ordering. So every element has an immediate successor, an immediate predecessor, and nothing in between, between them. So you must have those Z blocks. But now the fact is that if you order those Z blocks somehow, then this would be isomorphic to any linearly ordered set. So one of the things is that here I showed you that you can classify all models of the theory of the successor by the dimension. You just count the number of those Z blocks. Here, you can get any number of Z blocks, but on top of it, they can be ordered in any countable linear orders way. And there are uncountable many non-isomorphic ways of doing this. So this is a model theoretic mess. This theory is classifiable, then classify all models of it. This is completely unclassifiable because this is like classifying, for example, ordinal numbers. It could be any countable ordinal number, and you can have a model like the number. Okay, so this is what Stefan was saying, that these elementary extensions, they're much different from what we started with, but still the first order properties can present. So, and it matters in non-standard analysis. So that is a digression because, this is sort of in model theory, we have these general questions, but what happens in non-standard analysis, which is a big topic, or in AST, which is another big topic. But now if you have a real field, okay, and you go to an elementary extension, it's very non-isomorphic. This one is Archimedean, this one would be not Archimedean. If there are infinitely large numbers and infinitely small numbers, but still, what Karel can prove. Yeah, no, I know what you're going to say, but no, the language is for this, all you get in the language of fields, that's elementary extension. So this in the language of fields is the real closed field. So every polynomial equation of odd degree has a solution. So every polynomial degree of odd degree has a solution here, because there's also facts that are expressible in the language of fields. But now to do non-standard analysis, you do this elementary extension, but now the problem is that you have to select the language for analysis. You have to have functions, relations, and all kinds of things. So this becomes one big mess. But unless you do it in some set theory that has non-standard and that's already built into the language. But again, no, this is very non-isomorphic. This is Archimedean. Every number is less than some integer. And this is very much non-Archimedean. So still shows Archimedeanity is not the first order property. Okay, but no, but this is
interrupt.
No, we're not interrupting.
You say that you have these powerful theorems, these facts that you present on these facts, that you have compactness, and you have the elementary extendability, but these are also theorems in some theory, right? So
every theorem is this. No, I know what you're saying.
In the AST, for example, I am not convinced by this yet that you have these non-standard fields.
All right, no, that's absolutely
or
fine.
that you have compactness.
No, it's absolutely fine with me because I'm a model theorist. I don't care if you do not accept that much set theory.
Okay,
that's fine with me. However,
yeah, I'm just trying to pin down what is your background theory.
No, there is no background theory.
Come on. No. But so how do you have compactness?
No, because what I'm about to say, I don't need compactness. Compactness is useful and you use it when you need it. But for most things about countable models, and much of model theory is completely set theory independent, almost completely. You can have a very naive. You do proofs in very weak version of set theory, and surely AST is even too strong to do all of that. I told you, for example, no, I had this fact, the general fact that every structure with an infinite domain has an elementary extension, proper elementary extension. This is not equivalent to the axiom of choice, but because it's not really equivalent. I'm not quite sure if this statement, I don't know if Pavel or Karel know, if the existence of arbitrary elementary extensions is equivalent to the existence of ultra filters, because you do it in general by some kind of ultra power construction. And so you need some powerful set theory to do this in general. But for example, in arithmetic, what Scholem didn't work in any theory. Scholem's construction is almost. Yesterday I talked about not absence of computable representations, but if you're not a complete constructivist, you accept non-computable sets. And in models of arithmetic can be constructed by hand. You don't need the compactness. So, or what I was saying here, that if you have this structure, or here, this picture, you get a picture like this. If you apply compactness to this structure, you will get a picture like this. And actually, we get an uncountable picture if you do it fully set theoretically. But if I draw a picture like this with some number of those blocks, that there are parent-voice Frese games that are very kind of hands-on, that can be used to prove that you get an elementary extension. So actually, I'm showing you one. I don't need any basic theory other than some kind of really very naive mathematics. No, I do accept infinite sets, but I'm sure in AST you can do this. Pavel, you can help me here. Oh, Karel also. They can do this and much more in AST. So this is a very, if you couldn't do this construction in AST, then we would throw AST in.
Okay, so let's say I retract my question about the AST, but I am trying to pin down two things. So my comment had two parts.
What is AST?
AST is the alternative set theory that we will hear a lot of tomorrow and the day after. But you do have a background theory, right? From those statements that you tell us that
Now, look, I am a mathematician, and I'll go outside and ask any mathematician, what's your background theory? They will have no idea what you're talking about. They just do mathematics. But the fact is, but what we know is that what they do can be formalized.
Yes.
And so, like the reverse mathematics, there's a whole hierarchy of systems of second order arithmetic, and you can sort of gauge which theorem is proved from which axioms. This is a whole industry. So we do that, the logicians. No, but they don't like us that much. They do their mathematics. And and these theorems are actually fine. So far there's nothing wrong with those theorems. So you don't have to have those foundations. There is this thing I strongly believe in the fact, I come from Warsaw and I was in this department of foundations of mathematics. I'm very much for foundations. But you know what Kanamori wrote on his book on large cardinals? Do you?
I don't think the high.
I know what you mean.
Oh, the Kanamori has this sort of motto for, this is a book of large, set theory with large cardinal numbers and about the foundations and, this, and the set theory is supposed to be foundation of all of mathematics, and, this incredible edifice, a palace with towers and, incredible achievement, this and then you go down and down to the foundations, and you get to the foundations, and this is just cobwebs and spiders.
So I take it you tell me that you have developed your informal mathematics in such a way that it yields elementary extendability, right? Is that what you're saying?
No, I think I do what most people do, which means you take certain assumptions for granted,
Okay.
and you assume that such and such facts are true, such and such constructions work, and I see what else can be done with them. And but this is but your questions are actually very on the mark, because in 19th century mathematics wasn't like that, right? So one of the things, but ask, forget about what's your background theory. Ask an average mathematician what's a real number, and the answers that you'll be getting, will be kind of disheartening, because when I'm saying those things, we can, align at some point.
That's my question too. My question one was whether you have it. You have a background theory.
No, I don't.
Okay.
No, I honestly say though, I couldn't really. I just follow the flow. If one day it turns out that which could happen, that the ZF is inconsistent, then we will reconsider. But until this happens, no, there was some discussion about the role of foundations, and it was Marjorie Seneschal, who's a geometer, and she was one of the editors of Mathematical Intelligence. No, so she was kind of very much into sort of this mathematics for all and this and that. And she said, we're all aware that there are foundational questions. But she said, well, this is for logicians to do. If they find something there, they will tell us.
Thank you.
No, so we're working on trying to find something there. But anyway, so back to the grind here. And listen, look, so I showed you that.
So now I have 2 minutes, or it's over already?
Right now, it's up to you.
No, you were saying 2 minutes, and after that, we can ask whatever.
No, because I want to show the general picture, to show that there is some depth to what I'm saying. That I showed you that this is an enrichment of the structure, because the inequality, the ordering is not definable just from so it's a richer structure. You can define the successor function from the ordering, but you cannot define ordering from the successor function. But again, this is not a structure we're interested in. We know everything about this structure. It's not something that you want to study. The next step is what's called Pressburg arithmetic, which is already somewhat non-trivial, because this is the additive number thing. There are all kinds of things, all kinds of facts you express about numbers, that's what we're using on the addition. Okay. So the thing is that ordering is definable from addition. You say m is less than n if and only if there is some z, which is not 0, and m plus z equals n. Okay, so order, so addition knows perfectly where the ordering, no problem there. So you can ask, oh, how about defining addition from the ordering? And the answer is simply no. Okay, but how do we know? Again, because this is richer than just the successor. I have the whole ordering now. So, and there aren't very, there is a proof that is not much more complicated. I could show you the proof, but maybe you've seen enough proof already. In the style of what I was doing here, using automorphisms, that you cannot define addition from. But the reason is that this structure is called O minimum, from order minimum. And there's a theorem that says that all sets that are definable from the ordering are either finite or cofinite. You cannot define a set with infinitely many holes. And that's an interesting fact. You can think, oh, you have the ordering, maybe somehow you can define, okay, so you have the natural numbers, and it goes maybe a little bit here, a little bit here, a little bit here, a little bit here. And if you want to go to infinity, like if you want to define, for example, even numbers, this will be an example like that. The theorem says, no, we cannot do it just from the ordering. The only sets you can define from the ordering are finite or cofinite. So this will never happen. However, here, well, for example, the formula phi of x, which says there is this y, so that x is y plus y, defines the evens simply. Okay, so I define even numbers, not like that. So this, it follows, again, through model theoretic techniques, that you cannot define addition from the ordering. Okay, fine. So, and non-standard models come to play. This can be done in different ways, but non-standard models are used to prove this fact. Non-standard models of the order in simple ways. Now, but what about now? And the whole thing. Okay, so now here the whole hell breaks loose. This is like the most complex structure ever. Okay, but you can ask, well, is it really so anyway? So this is a proper expansion of the ordering because class is not definable. And there is a recursive definition of multiplication from the addition, but is there an explicit one? And the answer is no, there isn't one. But this is already, well, it follows in many different ways. But there's a theorem from 1960s of Ginsberg and Spanier that completely characterizes sets which can be defined in this structure. It's no longer all minimal, like this one. You define evens, you define odds, but every set that's defined here is eventually periodic. Okay, so there would be some initial fluff, okay, and if anything, some finite fragment, and after that, things will be periodic. Maybe there will be few periods. Maybe every third number will be, and every fifth number, which can be defined. Modular arithmetic comes into play. But with that multiplication, you define all kind of things like squares. Squares are not ultimately periodic. Primes are not multiple. These are lots and lots of things you define just with the, not even plus n times together, but just with times that you cannot define from the addition. So again, no, you get a richer structure. So now, is there anything more that can be said? And this is more kind of, is there anything else that's, there are continuum many subsets, relations on the natural numbers. So surely, most of them are undefinable, but are there interesting, things that you want to include, things you want to talk about, that are not definable from plus and n, because almost everything is computable sets, numerable sets, and it algorithmically produced set is defined in an extremely rich structure. But there is, this is Tarski's undefinability of truth. It's a celebrated Tarski undefinability of truth. What it means is this, that with plus and times here, you can code semantics. But first you code syntax. And for computer scientists, it was easier because computer scientists, the syntax is already arithmetized. What's inside the computer are the sequences of zeros and ones, and you manipulate sequence of zeros and ones, and then the sequence of binary sequence of zeros and ones can be coded by a single number. So this coding is an arithmetic coding. So you treat formulas and sentences as numbers. So either sub or something called truth. Sub is a satisfaction relation. When you numbers, truth is just a set of true sentences. So you can say, oh, there is something, this set. This is called Gödel numbering. You take sentences of arithmetic, these are syntactic objects, each can be coded by a sequence of zeros and ones, and that again can be coded by a single number. And you look at those sentences, this is my standard model, I will just call it N now. So that this is a true sentence. So this is a terrible set because it contains all theorems of arithmetic. If twin primes conjecture is true, it will be here. If the twin primes conjecture is not true, it will not be here. So this is a very, to define something, this is very kind of arrogant, because we don't know what's in it. We know something, we know many examples of those files in it, and there are lots and lots of files we don't know about. But still, it's a set. Okay, this is well defined. So we have all true sentences about arithmetic of natural numbers. And Tarski showed that this is undefinable for plus and times. If you put this if you add it in, it's a true enrichment. And actually, now there is the foundations of arithmetic. There is a whole industry, people who study axiomatic theories of truth. You go to non-standard models and you look at something. What are the sort of properties of this predicate here of this set? And there is a whole model theory of these structures. No, but to see how strong the structure is, because one wouldn't really expect this to be definable. However, you look at this set, the set of Gödel numbers of sentences which are true, and 5 has at most n quantifiers. So this would be like the truth up to n quantifiers. This set is actually definable for every n. Okay, so the truth actually, now think of this n being 2000. We've never seen a sentence with 2000 quantifiers. All arithmetic sentences have few quantifiers, but not an arbitrary number. So the truth is the union of all of those. This is similar to my first example, that you define the distance for every n, but you cannot define the total distance. So this is something, anyway, but this is very interesting. And with all kinds of applications also in set theory, and I'm interested in AST as well, how those things work. But that's a different story. But just to show you the depth of these things, it will go up and up and up and up. And but this is the arithmetic part of it. But it's kind of definability and enrichments in general. So that when you study fields, complex numbers, little closed fields, all kinds of other things, it's a big topic. So my goal was really to show you a little bit of what model theory does, and perhaps I will stop here and get exhausted. Okay, but I will gladly answer any questions, and we can discuss if there is time. So thank you for your talk.
I have a very primitive question. So I am this natural mathematician that somehow doesn't care about those symbols. We are just, for example, I was teaching measure theory, and first thing you are showing them there exists non-measurable set.
And
yeah,
okay.
So this is based on axiom of choice. So you can classify people for those who into those that believe into axiom of choice and those that do not believe. And I believe that normal mathematicians are those that believe into axiom of choice.
Okay.
So I haven't seen axiom of choice here somehow, but how it comes into your picture.
Okay. So one thing that maybe Karel will help me, because it's, if you really worry about the use of axiom of choice to produce a non-measurable set, then there are some results of Soloway and Shelah. The question is really open in set theory, whether indeed you need the axiom of choice to prove that there are non-measurable sets. So it's a technical, open, difficult question. There are models of set theory where all sets of reals are measurable. So if you worry about non-measurable sets, and I went to a talk by an analyst who said, all this nonsense, they would say, let's assume this or that is Borel, or, and then you prove things about Borel sets. Why don't we just assume that all sets are Borel? And because after all, you never encounter a non-Borel set. It will be, okay, every non-measurable set will be non-Borel, but if you want to do your analysis, you will never encounter a non-Borel set. So maybe
you have Tarski paradox, somehow.
No,
if every set is Borel.
But maybe we don't. No, the Tarski paradox is very troubling, so we should worry about it rather than accept it so eagerly. Maybe this isn't. Anyway, but do you have anything to add?
No, the axiom of choice is used, some form of it is used to prove that there exist Lebesgue non-measurable sets.
But it's always
model. Axiom of choice fails,
right?
But the axiom of dependent choice holds,
right.
And there are all sets are measurable.
Right. So then so these things are being studied, so that they can see it. It's not like no, but I would worry about those paradoxical decompositions of the sort of three-dimensional ball, and as Popielka did. Okay, so then maybe this is not necessary. And here, more people.
So show us. It will be useful to us. If every set is bored.
No,
this is the difficulty. You always have to say, let F be measurable, and then.
Exactly. So this analyst, I forgot his name, was saying, maybe let's make this assumption that every set is Borel. And in fact, analysis wouldn't change much. But it's set theory would.
Well, I would add to this, it's interesting that these students will accept it without even mentioning axiom of choice. I think this is one of the cheating we are doing on our students, that this proof of that there is a non-measurable set. I think we are showing them it in first year or second year. And without even mentioning axiom of choice, I think. So there is something that they will accept on faith. Or do you mention when you are giving the proof? You mention axiom of choice.
Yeah.
Okay, so you cannot. Okay, I see. I thought that you could say, it's like, how is it? No, you take the basis. No, you take the basis of the interval of the R over Q. No, that's the non-measurable set, right? And I think that they would accept it. That such a thing exists. Okay, they probably know that it depends on certain level. Okay.
Yeah, this is measure theory in the third year, say.
Yeah, I know, but
they already know.
I wondered whether there is really explicitly, because do they have at Matfis, do they have set theory now in third year maybe?
In your department, no.
In our
But
department,
I read it teachers.
I think now it's not obligatory. I think they can have measure theory without hearing anything about it. Okay.
So but when you do the Vitali set, then there is this point when you make your choices, and then you have this certain point, and but there are other constructions on non-measurable sets, and one is really comes from the well ordering principle that every set can be well ordered. If every set can be well ordered, you take the well ordering of the reals. And then you look at the two-dimensionally at this relation, and then you show that Cavalieri principle fails. So it cannot be measurable, and then it's kind of intuitive because you can see what like this set theory intervenes. And this was actually the most questionable part of understanding the history of how this sort of set theory was developing. That Countable was so excited about this idea that you can do this transfinite induction for arbitrary ordinal numbers, and what we really want to do in order to extend the inductive proofs to those transfinite inductive proofs that are in Borel hierarchy, are sort of everywhere. The Borel hierarchy goes all the way up to there's omega 1 levels. But even that probably is too much for analysis. Maybe you don't need all those uncountably many levels of the Borel hierarchy. So the other proof, I think, is nice because it's simpler, but we just says you violate the convention of Fubini theorem. And to define this set, you just will order the reals and do some kind of look at it from two different ways by looking at the answers. So by the way, but those are interesting questions, but those questions never bothered anyone, until the 1870s, or when I read some of Craig Smolinsky, the book when he talks about those developments, the pre-axiomatic developments in set theory, when suddenly somebody comes and defines a continuous lower differential function, and there was an outrage. But people said, no, who needs those functions? They said, we never really intended to study objects like that. They do not exist.
Recently, I used Sierpinski's theorem from 1910 or something like that. And this is a theorem where you have a measurable set, Lebesgue measurable set, that is half convex. So it means, that every 2 points, the middle point is in the set, and then it is convex in standard thing. But he needs this measurability. For example, after I used it actually for some function, defining the set, that this function is continuous. Because then you have somehow continuity coming from convexity somehow.
Yeah.
And I needed to prove, this was for function, to prove that the function is convex. You just prove half convexity, but you need measurability. You have to assume that it's measured.
No, I'm not disputing any of that. I think all those developments, and as I said, the Polish school, before the wars, functional analysis, Banach, and one of those things that they could do, this is all so fantastic, and we're not throwing anything away. But this model theoretic stuff is really different in a sense that it sort of brings things down a bit. And there are all kinds of interesting questions about really around definability of concepts. That, for example, taking a real closed field, or just a set of reals, the order set of reals the field, and add an exponential function. What I was talking about is the idea of all minimality. The real closed fields are all minimal. All the only things you can define are finite unions of Boolean Boolean combinations of intervals, and the exponential function, which seems like a natural thing to do. And for many years, with an open problem with this structure, it's actually minimal. And also you get decidability. The theory of real closed fields is decidable. What happens when you add the exponential function? And again, for those considerations, the axiom of choice that those things don't really matter much, but the model theoretic setup and logic that comes with it is actually tremendously exploited. So there are simply different directions of going. And set theory develops on its own, in kind of incredible heights of sophistication that I know very little about. Karel does. Well, sorry. No, sorry, I don't. No. Karel is a distinguished set theorist, so I'm just kind of, my specialty is model theory of arithmetic. And again, the talk wasn't about that at all, because there are all kinds of things happening there as well, but it will be a completely different talk about something else.
Is it somehow possible to generalize your results for the second order logic, or?
No, there's no compactness, but no, in terms of generalizing things from first order to second order, it's not just second order, but all kinds of, in model theory, the point is that we concentrate on classes which are put first order. So I said, I have a structure, I have a theory, and I look at other class structures that are models of the same theory. So those are elementary classes. And then you have these sort of tools. One of them is compactness theorem, and the other one is Skolem-Levenheim theorem that tells you how to build larger and smaller models. And there is a theorem of Lindström, who says that if you want to have those two properties in your model theory, then your logic has to have at least, it has to be first order logic. It's a characterization of first order logic in terms of model theoretic properties. So there are all kinds of directions now to get away from first order structures, and there are logics that are really even syntax free, the sort of abstract elementary classes. So you just study classes of structures, whatever they are, by whatever means necessary. So there is second order extension, but also additional quantifiers, infinitary logics. So this is all being done, and it's sort of just because first order is really not sufficient for description of, you know, in more complicated situations. Like, for example, in zero Banach spaces, logic is not working very well. There is some sort of continuous logic that is used, it's actually applicable to prove facts about Banach spaces or topological spaces. Well, those things are done, but everything is very technical. And first order logic has this natural thing of being extremely simple in its formulation. So, but things are done, but not most of the results do not transfer in any natural way.
No other questions? So thank you very much for the discussion and
Thank you.
speaker.